Again, in this lesson, we're going to be writing function rules. So let's look at an example. You can estimate the temperature by counting the number of chirps of the snow tree cricket. The outdoor temperature is about 40 degrees Fahrenheit, more than one fourth the number of chirps the cricket makes in 1 minute. What is a function rule that represents this situation? So the first thing we want to do is try to relate the two variables that we have in this problem. So we want to write a statement that kind of relates them. So we can say that the temperature depends on the number of chirps. Now, clearly that's not really what's happening here, but that's what we're doing. We're using the number of chirps to determine the temperature. So, we can imagine some sort of situation where you're without some sort of temperature gauge and you could kind of estimate the temperature based off of these chirps, even though really the cricket, I'm sure, chirps less when the temperature is lower. Okay, so that's kind of a relationship between the temperature and the number of chirps. We also want to define our variables. So let's let T be the number of the temperature in degrees Fahrenheit, and we're going to let C equal the number of chirps per minute. So how can we interpret this into an equation? We can write the function rule T is, so think about just like the statement here, temperature is, that's T is, 40 more than 1/4 of the number of chirps. I like to write the 1/4 chirps first, and then our adding 40, and that'll be our function rule for this situation here. Okay, another example. It says a landfill has a 50,000 tons of waste in it. Each month that accumulates an average of 420 more tons of waste. What is a function rule that represents the total amount of waste after m months? Okay, so let's go ahead. I'm going to go ahead and add a variable definition. I'm going to say that W is equal to the tons of waste in the landfill all told. Okay, so we have basically W, the total waste. We're getting more waste every month. We're getting 420 more tons per month. So that's going to be multiplied by the number of months. Because if it was 1 month, it would be 420. If it was 2, we'd multiply 2 times 420 and get 840. But then we still have to add how much there was initially. We're always kind of adding on some initial amount or something we began with. That's how you typically can identify something that's being added as opposed to what's being multiplied by our variable. All right, another example. It says a concert seating plan is shown below. Reserved seating is sold out. The total revenue from ticket sales will depend on the number of general seating tickets sold. So write a function rule to represent the situation. What is the maximum possible total revenue? So in the reserved seating, we have sold all these. So we really just need to figure out how much money we've already acquired. So there's 10 rows and 12 seats. So that's 120 seats sold. And at $25 a piece, we can total that there are $3,000 in sales already. What we really need to kind of eye in on is how much are we going to get from the general row seating. So if there's 30 rows and 16 seats per row, there's a total of 480 seats there that we can still fill with the general seating. Okay, so let's kind of dive into it. Here's the relate statement. The total revenue is general seating revenue plus the amount of the reserved seat revenue, or the price per ticket plus the number of tickets sold, or time, which is the price per ticket times the number of tickets sold. So let's let R equal the total revenue and let N equal the number of general tickets sold. So we can write our function rule that big R is equal to how much we're making per seat. So we're making $10 times each of the general seats plus all the seats we sold already, so that's the $3,000. So again, it's general seating here plus the reserve seating there. There are a total, as we said, of 480 more seats in the general seating. So if we substitute in and we use R is equal to 10 times 480 plus our 3,000, we'll get R is equal to 4,800 plus 3,000, or we can say that there is, $3,000, $7,800 in total revenue that is possible. Okay, another example, a kennel charges $15 per day to board dogs. Upon arrival, each dog must have a flea bath that costs $12. Write a function rule for the total cost for n days of boarding plus a bath. So again, you've got n days and then plus a bath. So you're thinking this is happening over and over again, the n days, and then the bath is happening once at the end. So let's define some variables. They already defined n as the number of days. So let's let C equal total cost. So C is going to be equal to how much per day? 15 per day plus our bath, which is one time, $12. So we want to figure out for 10 days. So 15 times 10 plus 12, that's 150. Oops, 50 plus 12. So we could say that C is equal to 162. So $162 for a 10-day stay. Now, would a 5-day stay be half as much? So if you think about it, it sounds right. Half the amount of time should be half the amount of money. But really, no, that's not going to work out because a 5-day stay will cost $87. This is not half of the 10-day stay because the flea bath. We're not dividing that 12 in half to get $6. You're still going to pay that $12. You're just going to pay half of the other part of the cost. Okay, now let's look at some nonlinear function rules. One situation that comes up a lot are area cases. So here we have a rectangle, and the area of the rectangle is given as area equals length times width. Well, that's great. That's a rule. That's a function rule for the area. But what happens if they tell us that the length is 5 more than the width? Now we can replace length with w plus 5. So when we go to make our calculation for this, we could start off by saying it's basically w times w plus 5, just replacing the L with a w plus 5. But then we could also distribute that and get w squared plus 5w. So that's another way to represent the rectangle's area. So what happens if we say we substitute 9 for w and find the area when the width is 9? So I'm going to put the formula here, w squared plus 5w. So that's 9 squared plus 5 times 9. So that's 81 plus 45, or in other words, 126 feet. Let's make sure we put the square on there. Okay. One last example here. Let's write a function rule for the area of a triangle whose height is 4 inches more than twice the length of its base. Okay, so our general formula for the area of a triangle is area equals 1/2 base times height. But what we're going with now is the fact that we're going to replace our height with the height is 4 more than twice the length of the base. So 4 more than twice the base. So twice the base would be 2b. 4 more than twice the base would be 2b plus 4. Okay, well we can go ahead and kind of distribute here. So I'm going to take 1/2 b times 2b. The 1/2 and the 2 are going to multiply to give me 1. And the b is going to give me b squared. So now we have to take 1/2 b times 4. 1/2 times 4 is 2, and we have the b there. So now that could be our formula for the area of this particular triangle. So let's go ahead and find the area when the base is 16. So area equals b squared plus 2b. So we have 16 squared plus 2 times 16 for our area. And so that's going to be equal to 256 plus 32. So the area is equal to 288 inches squared. All right, so we want to graph the function rule and determine if it's, well, they're saying, how do you know the rule is nonlinear? So kind of giving away part of that, but we can go ahead and confirm that. If we had 0 for the base, well, the area would be 0. If we had 1 for the base, 1 squared plus 2 times 1 is 3. If we had 2, we'd have 2 squared is 4 plus 2 times 2 is 4, so that would be a total of 8. If we had 3 for the base, 3 squared is 9, plus 2 times 3 is 6, so 9 plus 6 is 15. And then if it was 4 here, we'd have 4 squared is 16, 4 times 2 is 8, 16 plus 8 is 24. So we can go ahead and plot some of these 0, 0 here. 1 goes with 3, 2 goes with 8, 3 goes with 15, and 4 goes with 24. Maybe not super obvious, but you definitely would have to make a curved line there. You could grab a ruler for yourself and see that those are not in a straight line. So this is a nonlinear example. Another way that we could tell, other than from the graph, is when we look at any equation. If the equation has an exponent in it, that's going to be a situation where it's going to be non-linear. Now, technically, I think everything has an exponent. Everything has an exponent. So this has an exponent of 1. So I should really say it's an exponent that's other than 1. So here we have an exponent of 2. So that's another way to tell that it's non-linear. Okay, so now that you have those notes, you can do the problems on page 35. And